Hello, we are a three-person group for the CSE 320 Computer Networks assignment. The topic is TCP congestion control. I am Egemen and my teammates are Melih and Yunus. Our student IDs gave up the TCP Tahoe as the assigned algorithm. In this part of the video, I will explain the data structures and Tahoe code. Let me start with the header file. All our main data structures is in the node.hash. The first enum is called algorithm. It tells us which algorithm we are running, Tahoe, Reno, or new Reno. The second enum is CC state. It shows the sender's current phase, slow start, congestion avoidance, or fast recovery. Tahoe never uses fast recovery. Only Reno and new Reno use it. The neighbor struct hold the neighbor struct holds an ID, an IP address, a port, and a link cost. Read from the config files. The node config struct keeps the node's own ID and a list of neighbors. Now, the most important struct, TCP state. This is the heart of the simulation. It keeps the algorithm, the current state, the congestion window CWND, the threshold SSThresh, and counters for duplicate X and rounds. We use a double for CWND because congestion avoidance at small fractional values. Now, the last two struct, root entry and routing table, store the result of our Dijkstra algorithm. My teammate will explain the routing part later. Now, let's look at Tahoe code in node.c. The simulation begins with init backscore TCP. Wait a minute. Init backscore TCP. We set CWND to 1, SSThresh to 16, and the state to slow start. Now, the onBackScore egg function runs when a new egg arrives. The behavior depends on the state. In slow start, every new egg adds 1 to CWND. This gives almost exponential growth. When CWND reaches SSThresh, we move to congestion avoidance. In congestion avoidance, we add 1 divided by CWND. This is a much slower linear growth. Now, onBackScore duplicate backscore egg function. The onBackScore duplicate backscore egg function is where the three algorithms differ. We count duplicate eggs. The first two are just counted. On the third duplicate egg, we know there is a packet loss. Here is the Tahoe reaction. SSThresh becomes CWND divided by 2. When CWND goes back to 1 and the state returns to slow start. This is why Tahoe is called conservative. It throws away the whole window and starts again from 1. Reno is different. It sets CWND to SSThresh plus 3 and goes to fast recovery, keeping the window high. New Reno is similar to Reno, but also handles the particle X. Now, the on-time function. The behavior is the same as Tahoe's triple duplicate X reaction. SSThresh becomes CWND divided by 2. CWND resets to 1. State resets return to slow start. Now, let's run Tahoe. I will open the terminal. I'm using the triple duplicate egg event file from round 1 to 8. Slow start grows to window from the 1 to 9. Rounds 9 and 10 are duplicate eggs just counted. At round 11, the third duplicate egg arrives, SSThresh drops to 4.5 and CWND resets to 1. This is the Tahoe signature. From round 12, slow start begins again. At round 15, CWND reaches SSThresh and we enter congestion avoidance with linear growth. That is how TCP Tahoe works and reacts to packet loss. My teammates will now show the timeout scenario and compare Tahoe with Reno. Thank you.
Now I will demonstrate the congestion control behavior using three simulations. I will run TCP Tau under two low screen scenarios, then compare it with TCP Reno using the same event file. I will skip the node config and routing table. Those were covered earlier. Let me focus on the congestion control trace. As you can see, round 1 through round 8, each new AC key increases CV and D by 1. This is slow start. CV and D grows from 2 up to 9 as S stays at 16. So we haven't crossed the threshold yet. At the rounds 9 and 10, the first and second duplicate AC key is arrived. The algorithm is just waiting. CV and D stays at 9. Nothing changed yet. Round 11, third duplicate AC key. This is where TCP tau reacts. SS trash is cut in half. 9 divided by 2 equals 4.5. CV and resets all the way back to 1. State returns to slow start. 2 makes no distinction between triple duplicate AC key and timeout, but calls a full restart. Recovery begins from 1, runs 12, 13, and 14. CV and then climbs back to 2, 3, 4, still in slow start. At round 15, CV and reaches 5 and cross SS threshold of 4.5. The state switches to congestion avoidance. This time, we inject a timeout instead of duplicate AC case. Round 1 through 5, CV and grows from 2 to 6 during slow start. SS threshold still 16. At round 6, timeout. CV and D was 6, so SS trash becomes 6 divided by 2, which is 3. CV and D resets to 1. Recovery from 1 again at round 8. CV and D reads 3, which equals SS trash. The state enters congestion avoidance. Same pattern as the previous test. 2 always reacts identically to any loss event.
The previous part demonstrated TSP-TOW congestion control. In my part, I'll show how our program builds routing tables for the 6-node topology, how it chooses the shortest path using digital algorithm, and how messages is forwarded from one node to another in interactive mode. I'll start from the routing implementation in the source code, and then I'll run the program to verify the result in the terminal. The main function is build routing table. The function is responsible for creating the routing table of the current node. To do that, it first builds a graph representation of the whole network. Here, graph is matrix. It stores the codes between nodes. The nodes array keeps track of which nodes exist in the topology. At the beginning, the distance from a node itself is 0, and all other distances are initialized as very large value, which represents infinity. Then the program reads all 6 configuration files, from A configuration to F configuration. This is how it learns the full topology required by the assignment. And in here, for each neighbor relation, the program adds the link host to the graph. Because the topology is undirected, the same host is written in both directions. After the graph is built, the program runs Dijkstra shortest path algorithm. For Dijkstra algorithm, this stores the current shortest known distance. Pre stores the previous node on the shortest path and visits marks nodes that have already been processed. Source nodes start with distance 0 and all other nodes start as infinity. Whenever the algorithm finds the shorter path, it updates the distance and records. The previous node, later the previous node information, is used to reconstruct the full path and determine the next loop. And in here, finally, the routing table stores the destination, the next loop, total cost, and the complete path. This information is later used when the node needs to forward a message. And now let's run the program and check whether the routing tables matches the expected results for node E. This is the routing table for node A. The most important lines is the rotate to node D. According to assignment, node A should not use direct link to D, because the direct cost is 13. Instead, the short path is A to B to D. The cost from A to B is 4, and the cost from B to D is 8, so the total cost is 12. As you can see, our rotating table correctly selects B as next hop for destination D. And also I want to show how we send messages from A to D. As you can see, we sent the messages from A and B forwarding messages from A to D. You can see in log, and D is received messages from B. Thank you for listening to me.